Hello, welcome to this part 2 of this introductory lecture on engineering geology and rock mechanics. In the previous lecture, we discussed how engineering geology developed as an independent subject, what was the need to have engineering geology as a specialized subject, and what are its uses and how we can actually use geological knowledge for safe, stable, civil, petroleum and mining construction and excavation. We also went through the procedures and codes for estimation of uniaxial compressive strength and tensile strength of rock samples. Now, UCS and tensile strength, they are widely used as input parameters in design of excavation and construction. In rock mass classification, UCS is used as a direct parameter, while in Q system given by Barton, UCS and tensile strength, they are indirectly used to assess SRF values, which stands for stress reduction factor. Now, the lab tests prescribed for UCS and tensile strength require us to have cylindrical rock core samples. However, retrieving cylindrical rock core samples can be expensive and requires expertise. The sample preparation is also tricky. So, it happens that most of the times we don't have cylindrical rock core samples to conduct tests on. However, there is a test called point load strength test, which can be conducted on pieces, lumps of broken rocks, which gives us a fair idea about the uniaxial compressive strength of the same rock. There have been ample researches which have been conducted on the correlation between uniaxial compressive strength and point load strength of the rock material. The point load strength testing entails putting a piece of rock, it can be a core sample as well, between two conical loading plates, and gradually the load is increased until the sample reaches failure. Here the mode of failure is under tension. The point load strength, or simply IS, is calculated as P by dE squared, where P is the load at failure while dE is the equivalent diameter, or in case of diametrical test for rock cores, cylindrical rock cores, it is the diameter of the rock core. So, P by D squared, and it's denoted in MPa, megapascal. Beside rock cores, cylindrical rock core samples, any lump or rock of any shape can be employed for testing the point load strength. What changes is how we calculate D, which is essentially the distance between two loading plates in case of diametrical samples. For an actual sample of a cylindrical core, the equivalent diameter is calculated as an under root of 4a by pi. So, we assume that there is we assume the load is acting upon a circular cross section, and we calculate the area and its equivalent diameter for that area of a circle is calculated, which is used for calculation of point load strength. For cuboidal samples, we need to know the distance between the loading plates at failure and its width. If it has different width, we measure the mean of the two widths. So, the area for the sample would be W, that is width, multiplied by D, that is the distance between the loading plates, divided by pi. And using the formula pi r square equals area and computing it for diameter, we can get the equivalent diameter. The tests, they need to be standardized. Like most of the UCS tests, they are conducted on 50 millimeter dia core samples. Hence, there is a size correction which has been retrieved empirically for lumps. So you calculate their point load strength. Then using this size correction formula, you can get the equivalent point load strength index for a core sample of 50 millimeter diameter. So the point load strength for a core sample of 50 millimeter diameter equals the point load strength of the core sample multiplied by equivalent diameter, which is under root 4a by pi divided by 50 raised to the power 0.45. Now, like I've said, there have been many correlations which have been established experimentally for the correlation between uniaxial compressive strength and point load. The most common one being UCS equals 24 times point load strength index. So if the point load strength of your rock material is 1 MPa, then you can safely assume that the uniaxial compressive strength of the rock material would be 24 megapascal. There have been different researchers which have conducted research on different rock types. So usually the correlation coefficient for point load to UCS conversion is lower for weaker rocks and is higher for stronger rocks. The testing code prescribed for point load strength test is ISRM 1985 and ASTM D5731. As already mentioned, for cylindrical core samples and when the tests are conducted diametrically, the equivalent diameter is the actual diameter of the core. And for core sample, the prescribed diameter is between 30 to 85 millimeter. And also, the rate of loading should be such that the specimen fails between 10 to 60 seconds. So it should not be delayed, as if the rate of loading, if it's too slow, then there will be indentation and you will get inaccurate values. Also, another important thing is at least 10 tests should be conducted for estimating the point load strength. And the two end values should be discarded and an average should be taken. These days, researchers actually use all the values and present it as a histogram. Now, I have a problem for you. Here, you need to assess the disparity in point load strength when a cylindrical rock core sample has been tested axially and tested diametrically. As you remember, the formula for calculating the point load strength is P by D squared. And DE, equivalent diameter in case of diametrical test, is equal to the diameter of the core sample. However, in the axial test, you need to find the equivalent diameter. Here, you'll multiply diameter of the core sample with the distance D between the loading plates at failure. Then you will find the equivalent diameter of this area, which is using under root 4a by pi. And then you will calculate both axial point load strength and diametral point load strength, and you will see what is the disparity, what is the anisotropy in the calculated strength. The prescribed codes for conducting tests using Schmidt Hammer are ASTM D5873 and ISRM 1978B. It is recommended by ISRM that the tests which are valid for Schmidt Hammer rebound numbers should have a range of UCS between 20 MPa and 150 MPa. So, if a rock material has a strength less than 20 MPa, then it won't be valid if we follow the ISRM code. However, ASTM allows us to conduct rebound tests on rock material having a strength ranging between 1 megapascal and 100 megapascal. Uniaxial compressive strength and Young's modulus, they have been widely correlated with the rebound number. And again, there have been correlations, the standardized correlationships between unit weight of the rock material, the angle or the inclination at which you are applying or using the rebound hammer, and the rebound number together with corresponding compressive strength. There are two types of Schmidt hammer, L type with an impact energy of 0.735 Newton meter and N type with an impact energy of 2.207 Newton meter. Prior to 2009, rock engineers or engineering geologists usually employed L type Schmidt hammers. However, as of 2018 or starting from 2009, engineering geologists have been using both L type and N type Schmidt hammers, which was previously used mostly for concretes. Here in this graph, you can see the correlation between inclination of the Schmidt hammer with respect to the surface, unit weight of the rock material, and uniaxial compressive strength. Now, the estimation for UCS based on rebound number are to be done with respect to the unit weight curves. So, you will have a different UCS value for same rebound number if you have a rock material with a unit weight of 20 as compared to a rock material with a unit weight of 26. Another common test which is routinely conducted is Slake durability index test. So, what is slaking? Slaking is essentially the dissolution of cementing material in rocks. It's mostly pertinent for sedimentary rocks. So, what usually happens is if you're constructing a dam or if you're expecting your construction or your lithology to be submerged under water, then you should know its slaking durability, which is again the potential or resistance against dissolution of cementing material in a rock. The Indian code for Slake durability index test is IS 10050-1981 and the ASTM code is ASTM D4644. The test requires brass drums which can be rotated at a rate of 20 revolutions per minute for at least 10 minutes when partially submerged in water. Again, you would require an oven so you can completely dry your samples at 105 degrees centigrades and weighing machines. So, for this test, what we usually do is we first prepare the samples, as in we have lumps, we try to make them spherical, as in we remove the sharp edges in them, and then we mostly take around half a kg of samples, that would be 10 pieces if each piece weighs 50 grams. We heat them up, we put them in those drums, we submerge them in water, then we rotate them. By rotation, we are actually agitating them and a certain amount of friction is being induced. Then after that, they are weighed again, then dried again, and we measure the loss in mass after agitation and being submerged in water. So each cycle consists of around 10 minutes. The Slake durability index after 10 minutes would be C minus D divided by A minus D into 100, and it's given in percentage. So where C would be mass of drum retained after the second cycle, D would be mass of clean drum, A would be mass of drum plus dried samples, and D again mass of clean drum. There have been classifications given by Gamble, which correlates the retained weight and durability. So if the percentage retained after second cycle ranges between 98 to 100%, then the durability of the rock material against slaking is quite high. On the contrary, if the retained percentage lies between 0 to 30%, which is true for some sedimentary rocks, then the durability is quite low. So this was the first lecture on introductory engineering geology. In this lecture, we have discussed the origins of engineering geology, the use of engineering geology, assessment of strength parameters, their direct means and indirect correlated means. Thank you once again.